Okay, good morning, and let's come to another topic, the particle physics. And Dima gave me a very challenging task that combine the stand model and some new physics. So I want to make a balance between the coverage and the depth. So probably I will use my first lecture to be some fundamental topics about particle physics, about the STEM model, some fundamental calculations probably, and using my next talk for some new physics, different. But I will cover some of the neutrino physics since I'm majoring in these parts. Okay, then here I used the Russian translation of my name. I don't know if it's correct or not, but I used the dipstick to make the translation. So yeah. Oh, then this is what's the STEM model for particle physics actually. In our world, actually, it's a framework, theoretical framework, actually beautiful structure to describe the fundamental constraints and also their interactions. And it's based on the symmetry argument that using based on the quantum mechanism and also the Lorentz invariance and also the most importantly the gauge invariance actually. And then based on some different structure, the Lie group structure, the SU3, SU2, and U1. This is to describe the strong, weak, and all electromagnetic interactions. And here is the formulation of this on this weak and electromagnetic, the unified theory of this, the electron-weak theory. I will come to this in my later parts. And this is proposed actually by the so-called Weinberg, Glashow, and Salam actually. And within the STEM model actually the building blocks are mostly the fermion is to make up the matter, and then some force carrier as we just force carrier about from gluon to photon to, and also the weak force carrier, the W and Xeon. And finally, the very crucial role of the Higgs boson to give the mass to the fundamental particles. I think at first we know it's not give the mass to our matter, our Euro matter, but only give the mass to the fundamental fermions. Okay, then also for this model, not only the blocking blocks, but they have connections or they have relationships. Here, for this diagram, show the different relation. The connection means they have interaction with each other from the fermion to the different force carriers, and also in particular for the Higgs boson, it has its own so-called self-interactions. Actually, you can see here that they have a circle connect to itself. And then this is my outline for this. I will firstly give some fundamental talk about the particle interactions. Then for these three parts of this STEM model, from the circle part, from the outlet part is fermions, and then inner part is force carriers based on the gauge invariance theory, and finally the Higgs boson to build up the current unified electron-weak theory. And finally, next day, tomorrow, I will tell us about the several possibilities to go beyond STEM model. Yeah, the fundamental interactions actually we have four. We all know this. As Jonathan mentioned, the gravity tells the dark matter existence, and in the particle physics part, actually we mainly focused on the other three parts: the weak, strong nuclear force, and also the electromagnetic force. Actually, they are the role they play their important or unique role in different phenomena. You can see from beta decay to the constant bending the print to from the atomic force, from the strong force, and also what we all know in our ordinary life in the electromagnetic force. And for these three fundamental parts of this star model force carrier, actually the strong electromagnetic and the weak vortex, you can see they are carried by their carriers from the photons. It's the most known one, and then later I will introduce the weak interaction carrier, the W and the Xeon, and then the gluons. They have different interaction range. For example, for the strong and the weak interactions, they have very short effective range from, you can see for strong interactions, it's in the atomic, in the nuclear size, so it's in the 10 to minus 15 meter, it's a fermion size. And for the weak interaction, it's even shorter distance. And for the other two, it's long range force. It can go with square inverse of the R square, actually. Yeah. And also, I would like to mention is that the strength, the interaction strength. For the electromagnetic part, we know this is alpha 1/137, and for the weak interaction type, we will show its interaction strength is at the Fermi constant, the GF, so it's the level of 10 to minus 6, and for gravity it's super weak, and it's 10 to, here it's written as 10 to minus 38, but it's super, it's in the very tiny length. Okay, then usually we, to represent the force carrier or the interactions, usually in the fundamental particle physics, we use it for the Feynman diagram. Usually there are several examples from the electromagnetic interactions to weak interactions and strong interactions. You can see with the carrier, force carrier of photon, and also the Xeon boson, boson for this is for the beta decay, I will show it later. And then with exchange of gluons, you can see there is the nuclear interaction, the strong interactions. Actually, usually there are some instruction to make this Feynman diagram. For example, the outer part is a straight line to represent the initial and the final particles, and antiparticles are also shown, but with different directions. And then the intermediate part, the photon usually in the wheel parts, and the heavier boson use some the dashed, and for gluons since it's confinement and property, so you already use this special symbol to represent the gluons. And actually, there will be some vortex to connect the different particles, and the vortex will represent tell you the interaction strength, the coupling constants in the fundamental part, particle physics interactions. So it's in this way. Then, by using the Feynman calculus or other tools, you can calculate the interaction cross-section of different interactions, and then you can make a comparison with the experimental measurements. So this is what we do in the experimental high energy physics or particle physics. So here you can see there for different interaction part. For example, we take some example for this electron positron annihilation to the pair of the muon and the antiparticle and anti-muon. You can see this is a tree level in the electromagnetic interactions, and also there will be some high order corrections with some loop factors. And you can see for the for the electromagnetic interactions, since is quite perturbative, so the dominant contribution will be the tree level contributions. You can calculate this, and this one will give you a subleading effect. Yeah, this is one question I would like to show. This is a question, exactly a question in this Big Bang theory, and this is a quiz to calculate the cross-section of this electron-positron in relation to the muon pair. Actually, this Sheldon cannot solve this question and want to change to another one. But here we only have part of this. This is a Russian scientist as a teammate of Sheldon Lee, Glacial, and actually he exactly speak out the final solution without any calculations. So I think you can calculate this very easily as a Russian. Yeah. And also in the final stage, I also give you another exam or homework to calculate another cross section related to neutrino and electron scattering. It's also at the tree level you can calculate this. Okay, and in particle physics, usually we are using the natural unit to make the Planck constant and the space-level light to be 1. Then you can convert different units by this different combination of the constant. So, for example, I think in the morning, John also mentioned this for this unit conversion, it's around 200 MeV times fermion to be 1, and you can make any kind of different combination to convert different units in the standard unit to this natural unit. Okay, and then it's another powerful tool is you can do the dimension analysis without making very careful calculations. And this is also applicable to the natural unit, or sometimes people call it Planck unit. And then for example, all the quantities can be measured in the unit of energy or mass to some power. For example, the m, the mass, the momentum, and there will be the power, the positive one. And you can also tell others the power of the units by using the action, since action is dimensionless. So then you can change, for example, the distance and the time is unit of e minus 1. So then you can calculate the dimension of your Lagrangian density is e to power of positive 4, and you can convert to other quantities. And for example, we will show it later. For the mass term, you already have the dimension of mass. This is by definition for this dimension analysis. So you can calculate, for example, this is free, I think, QED equations. You can show the mass term, how it's the dimension of mass, since the fermion have the dimension of 3/4, the 3/2. So, and also you can calculate the dimension of the electromagnetic fields. Then, we can come to our main part of this. And first, I will tell you about the 3 generations of fermions. And sorry. Actually, this the small particles are a long journey from back to more than 1 century from the discovery of electrons, the first fundamental particles, and then it's actually confirmed by G.G. Thomson near, it's before 19th century. And then for photons, from the Einstein conceived its existence, and the Compton scattering process proves its existence. And then for muon and others, you can see actually from this plot, this is from their series chart or conceived to the discovery. You can see really we are in the golden stage in this period, since the new particles are were discovered in a very short time and very frequently. This is the best period from the particle physics point of view. And then this is first generation fermions. Actually, our first generation fermions are the real building block of our world or our matter, since our atoms are made of the protons, neutrons, or made of the first generation of quarks. I will show it later. And then for also the electrons and also it will intermediate by photons actually. So it's also interesting that the electron, proton, neutron are discovered by these three gentlemen. Actually, they are in the same school. They are the teachers and the students in this level. J.J. Thomson, Rutherford, and Chadwick in the British. And then the neutrino. Oh, sorry. Neutrino is the first generation neutrino is the electron antineutrino or electron neutrino from the beta decay. Actually, it's conceived by Pauli, and then experimentally detected in the reactor neutrino experiment by Cohen and Rins. Actually, yeah. Then I think in the later stage, talking about neutrino physics will explain this. I think neutrino physics, the existence of neutrino is proposed by Pauli because of the energy non-conservation and also the momentum non-conservation, to propose one new particle to carry out some additional energies and carry out some spin, so the carbon-14 spin increases also. So this is the first generation of fermions, and second generation of leptons. Then in 1930s and until 1960s actually. So you can see the Anderson discovered the muon from the cosmic ray. So this is in 1936. So it has the identical properties, interaction length with electron, but with a mass of 200 times heavier. So, and then the associate neutron particles, the neutrino, actually, people will ask, will this neutrino is a new particle or the same particle as in the beta decay? Actually, some indication in 1950s by Feinberg showing that if the neutrino from beta decay and together with muon is the same particle, actually they are not consistent with some observations. For example, the muon decay either to the, for example, E gamma actually is a higher rate if they are the same actually. And so they conclude that they should be the two different particles. And in the meantime, I think the famous Bruno Quantico proposed how to detect the muon neutrino, and the muon neutrino should be another particle. So it's for this symbol, you can very famous, I think, in particular for Russian colleagues. And also, Li and Yang also proposed this muon neutrino as a high energy neutrino beam to test different properties of the particle itself and also the Stein model interactions. And then two years later, 1962, in the Brookhaven, the Steinberg, Leon Ledman, and Schwarz actually really measured the muon neutrino to be a new particle different from the electron neutrino, since they cannot connect to each other. But when we come to neutrino oscillation, actually they have some tiny relation with each other because of the interference of the different mass state. This will be another story for tomorrow. And then the second generation quarks is also very fruitful result in 60s. Actually, we know from pion and kaon, from pion, charged pion, we know it's made of the up and down quarks and antiquarks. And after the discovery of K meson, actually we need a new quantum number to explain their production and decay properties. So this is a strange quantum number. And then in 1964, German and Zweig proposed a strange quark. Actually, it's different with different properties. Actually, it's a down type. Yeah, it's the fractional charge. So this is a new era of the second generation quarks. And then the same year, actually, Glashow and Bjorkin proposed the charm quark as a pair to the strange quark with the different fractional charge. But actually, the dynamical reason why we need the charm quark is because of the GM mechanism in 1970s, because it will suppress some decay modes of the kaon decay to for example, the pure lepton decay. Only with charm quark we can suppress it because of the existence of this the famous GM mechanism. This is the existence of the charm quark, and then 4 years later, the famous G psi particle was observed as a pair of the CC bar, the germanium particle, and actually with two different experiments. Pardon? Okay, and actually it's named. It has a famous name, the November Revolution. Yeah, I think it's because it's in US. It's very important and very popularized. Actually, I think, yeah. And then we come to why we need the third generation of fermions, and actually we still need to go back to some period, the parity violation. I think this is proposed by Li and Yang to explain the theta tau difference of actually this have different decay mode, but with very same mass. So I think the Li and Yang propose in the weak interaction part, the parity is not conserved, because in all the previous experiments, they cannot prove they are conserved because of the always measure the so-called for example, the scalar quantities of this beta decay. Not, for example, they need to measure the pseudo-scalar quantities. So they propose different ways to prove if the parity is conserved or not. And the Madam Wu, CS Wu, using the magnetized cobalt 60, so all the spins of this cobalt nuclei is in parallel. So then, if there is particle violation, the angular distribution of these decay particles, the beta particle, will be different. So this proved that the parity is violated, and also is maximally violated. Actually, this is the foundation of the state model for the weak interaction, and also for our later stage of the CP violation. Since when at the very early time, people conceived that parity, charge, and T are all invariants. But after the parity violation is observed in weak interaction, there is also conceived that CP may also be conserved or violated. And after several years, in 1964, the K-meson decay proved that there is a CP violation at the size of 1/500. It's a very tiny violation of the CP violation, different from the maximum violation, order of 1 violation of the P parity. So this is evidence of the asymmetry between matter and the antimatter in the weight interactions. So how to explain this CP violation actually is a mystery at that stage. And the first successful idea is just the motivation to have 3-generation fermions. That is Kobayashi Masukawa conceived that there is a very good or beautiful CP violation mechanism I will show it later for the CKM matrix. And they introduce from 2-generation to 3-generation to introduce 2 additional quarks. Then there will be from 3-quark model to 6-quark model, and to have the 3x3 mixing matrix. So in this way, they can have intrinsic phase in this mixing matrix, and this a complex phase will play a role to explain the CPU violation observed in the key meson and the future in other system, meson system, and currently in some Baikal system, in particular in the HSP experiment, I think this year. Actually, then there's two additional quarks also was observed. One is 4 years later by Leon Ledman in Fermilab, the bottom, and then in 1995 is long-awaited final top quark, since it's much heavier than the people conceived. So it's only observed 20 years later. And there's a story that Masukawa, how his books say that he has this idea when he takes shower in the base tube. So this is inspiration from this particular event. This is in his book. Yeah, very interesting. And then finally, the final moment for the building blocks for the fermions. This is the tau lepton is also discovered in 1975 in SLAC by Martin Pro, and also the final 3-generation fermions, the tau neutrino, is quite difficult to observe, and finally we see it in this century, in 2000, also at the Fermilab. So then we complete all the zone of the 3-generation fermions, and with all the 6 leptons and 6 flavors of the quarks. And so this gives us an opportunity to make this kind of plot, that all the fermions are in the edge parts, and then it will be our matter particles, and the inner part will be force carrier and the Higgs boson. And then people will think, why we only have 3 generations, why not 4? But after a long history of the search, I think now we don't have evidence for any kind of 4th generation of the quarks or leptons. And then why it is for this particular number of 3? Actually, for our spatial space, also we have 3 dimensions. So in this paper or talk, I think Max Tenmark at MIT have some argument, his personal argument, why we have 3 number of the spatial dimension and 1 number of the time dimension, because of different arguments, stability or tachyon or other things. So for our material world, why we have 3 generations, actually is also all our matter world, I mentioned, only made of the 1st generation. So the 2nd and the 3rd generation fermions actually are either from the cosmic, for example, muon, or from they are very short-lived, so can only produce from the collider or other experiments or in the lab. So there is this existence actually because of we need to have some beautiful or good, not only the particle itself, but the conversion between different particles to explain a different phenomena in the world. So not only their building blocks, but their different converting process or interactions. In particular, as I just mentioned, we need to explain the asymmetry between matter and antimatter. So we need the CPU violation. So this could be one of the strongest evidence or argument why we have these 3-generation fermions. So then we will come to the next part of this presentation. So now we have the building blocks, but we also need how we organize their interactions, or how we organize their roles as their converting part convert to each other. So this is in the current language or the current model, Zen model, they are all organized by this simple principle and the gate invariance theory. I will using some time to explain this. So this is many of people using this word, the symmetry determine or dictate dynamics. So to explain how we organize the interactions in the modern era. So this is from the Galilean principle of the relativity to the current modern special and general relativity. Actually, all the physical laws have the same form under this different form of space and time transform. So this is when some symmetry determines the physical laws from the Newton dynamics to the special and general relativities. And it's also true in our fundamental particle physics part, the gauge theory or gauge invariance principle to determine the interactions. The first is the abelian part, the U1 proposed by Wayne. Yeah. And the principle is very simple. Yeah. To ensure the Lagrangian of the electron field is invariant under some spatial and time dependence phase transformation in the interspace part. So we need to introduce, even we start with the non-interacting Lagrangian, only for example, Fermion and some boson. And the gauge invariant will make them to be interacting and to maintain the formal invariance between all the full Lagrangian. And this is the gauge invariance theory or gauge invariance principle to determine these interactions. So this is also the role of the QED, quantum electron dynamics. And also it will require the force carrier to be massless to respect or reserve the gauge invariance. And also the same also true for the non-abelian case. It's proposed by Young and Mills in 1954. It's also our main principle to build our standard model, the non-abelian gauge theory or Young-Mills theory. It's also the generalization of the abelian case, but based on some different group, for example, non-abelian group, SU2 or SU3, or even in some unification theory, Grant unification, you can build on some even higher gauge group. I may mention it in tomorrow. Yeah. Yeah. For this local or localized or local gauge theory, it's important because this will give you some additional field, dynamical field, to describe their interactions. For the global ones, actually, as shown in this, the global phase is unobserved in the quantum mechanism because we only observe their modes. And then the abelian theory is, since we want students to follow this, I use some equations to show this. For example, the U1 gauge, the QED Lagrangian, this is Fermion. The mass sum, this is kinetic sum, and we need to introduce a current derivative rather than the normal derivative to put it here. And this is the kinetic term of the gauge boson, or so F mu. And so we need to make this space-time dependence transformation for this Fermion and for this boson. And then we require the full Lagrangian to be invariant under this localized gauge transformation. And then it's very simple to make the calculation. You can see here this since this F mu only derivative and anti-symmetric, so this additional term will be cancelled. And for this mass sum also, since it's a phase and you have the conjunctive field, so they also so this phase also cancelled in this term. In particular, in the middle part, the first term will have additional derivative of this phase, space-time dependent phase, but we can also have this additional phase in the field, in the A field transformation. So finally, these two terms will be cancelled. So then we will get an invariant theory, gauge invariant theory of the abelian or U1 Lagrangian, starting from the free theory without interaction, but finally we are finally how this interaction of this actually derived from the current derivative. So this will give us the interaction between the gauge field and the fermion, this part. Okay, so the QED is very successful, even considering the current, the latest GMAS2 or measurement, the stand model. And it's not only, in particular, the current GMAS2 not only rely on the QED, but also some QCD calculation. But in the very early time, actually, I would like to say that the theoretical calculation, prediction, and the measurement are consistent after more than 10 digits of the numbers. Actually, even the QED correction is also in the level of, I think, 1 over 1,000 is that level. So that means it's very accurate, and it's for this itself, it's a perturbative theory and can be used to make very accurate predictions. So then we can use some example to show how it works. And this is a scattering process between the electron and the nucleon, for example, the proton. And their interaction strength is determined by this gauge principle, the vector parts of these fields with fermion. So then if we have this interaction part, and here the coupling constant is just the electron charge. So by using this, actually we can calculate the Fermion diagram by using this simple rule. And this diagram describes this interaction exchange by the virtual photons. Yeah, this is a basic diagram to calculate this process. And we can do it even simpler by using the fundamental particles, the scattering of the photons and the electrons. So this is the rather simple Compton scattering process and this is totally calculable. So it's very easy to make this calculation. And we can give some order of magnitude estimation for how this can be done in an accurate way. For example, the vortex of this is roughly, since the electromagnetic interaction has the range of alpha. So this vortex, the coupling constant, is the level of square of the alpha. So for the higher order calculations, and it's 1 loop and 2 loop, you can only count the vortex since it's very small. It's a small value, small parameter. So you can just calculate the M1 if it is order 1, and the 1 loop calculation or 1 loop contribution only. Oh, sorry, I reversed it. So it's only the alphas and alpha square. So that means the 1 loop correction is smaller than 1%, and the next to linear order is even smaller than 10 to minus 4, even 10 to minus 5. So this is ensure the accurate prediction for this QED. And then we can come back again to the main process is mediator of the photon. But if the scattering particle, for example, here it's a proton, is not a fundamental particle. It's composed other quarks or other particles. So in this way, to make reliable and accurate calculation, in particular for the high energy parts, high energy process, the high order correction for this vortex, even produce other new particles for this scattering process will come in. So we'll rely on the quantum Chromodynamics, the QCD, to describe the strong interactions of this process. And this will need I just mentioned the Yang-Mills theory or the non-abelian gauge theory. So it's just a generalization of the U1 gauge theory, but 2 or 3 points need to be careful is and how to organize self to respect the gauge invariance. For example, how to organize the field strings to be when need to add the additional term, the nonlinear term in this form, and also we need to define this derivative in this way, and then how this strings field transform under this localized gauge transformation. So under this part, all the Yang-Mills Lagrangian, the free part of this will be invariant under this gauge transformation, and will give us the interaction because of this term, and the derivative term will give us additional interaction between this gauge field and the fermions. And but at that time, this non-abelian theory is not well accepted because this is based on to describe the strong interaction between proton and neutron. As the isospin, you can see here, this fermion is organized as a doublet of the proton and neutron, the isospin doublet. And then the gauge invariant requires the intermediate gauge boson to be massless, but we all know this the strong force is localized. It's within the nucleon. It's within nuclei. Sorry, in this form. So these have some contradiction with each other. So it cannot. This simply describes the strong interaction in this way, but it's a fundamental part to organize the future QCD and even the electron wake theory. So this I will have a very simple homework that proves that the gauge symmetry is not respected for this mechanism. So it's you can prove that if there is a gauge invariance, the mass term of this gauge boson should be vanishing. Okay, before I go to the electron wake theory, I will take most of the time to be for this, but I will mention some basic ideas in the QCD, since this is quite difficult to make real calculation because of the non-perturbative property of this. But I think I would like to raise the basic concept of this QCD for our particle physics, or for this how to make up the hadrons and also others. So QCD is based on it's a strong interaction theory of quarks. Actually, it's proposed in 1970s, and actually the experimental foundation of this is the deep elastic scattering in 1968 or also 60s, and I think Baikal proposed the scaling properties of scattering behavior indicates that the nucleon inside the nuclei is some point-like particles, and so this is an indication of the quarks, or in the Fermion language, he uses the parton particles. So the quarks will be responsible for this quantum number of the proton neutrons. For example, this usually we call it valence quarks, but the nucleon is not only composed of the valence quarks or antiquarks, but it's how the quark sees. It's usually named as there will be particle, this is quark or quark and antiquark pairs, and even the gluons inside the nuclei. So it's a very complicated system for this. even in the current research, it's a particular area need high computing power to make any kind of predictions. Then the quarks I mentioned, we have six different flavors, up down for the first generation, and charm and strange for the second generation, and the top and bottom of the third generation. So usually we call it flavor. Yeah, it's same as the leptons. And one important part to build the QCD is not only the flavor index or flavor degree freedom, there is additional degree freedom or different index for quarks, that it will be the colors. That means for one particular flavor of quarks, actually they have three different types of these quarks. So, and also the free quarks has never been observed because of confinement. I will show it later. So, but colors, why we need colors? That there is some crisis or problem in some different the hadron particles. In particular, for this Data++, actually it has spin of 3½ and consists of 3 up quarks. So that means it will the valence quark of this is 3 up quark with parallel spin. So if there is no additional freedom or no additional parameter to make it antisymmetric, actually this will be forbidden by the Pauli principle. So this is the problem, statistical problem of this particle, and I think in 1960s people proposed the color degree freedom to distinguish these three different quarks, three different up quarks. And so this gives the solution for this problem. And also the foundation for the QCD. So QCD means quantum chromodynamics, means the color. And in addition to three different colors, this is based on the QCD built based on the SU3 gauge theory, SU3 group. So the intermediate boson will be in the adjacent representation. So it will have it will have 8 different gluon in the intermediate boson. So it's 8 type of the gluons. So each gluon carry their own color. So that means the gluon will have the self-coupling or self-interaction. Photon don't have, since it's neutron in the U1 theory. Okay, then when we have gluons, we can calculate different interactions of these. For example, quarks mediated by the gluon, and also the scattering of these quarks with gluons. Yeah, here, and we have this Lagrangian similar. Just the same as SU2, but the index by change the Pauli matrix to the gamma matrix. Yeah, here the very unique role of the gluon is it have their own self interaction. For example, the 3 gluon or 4 gluons. So this is additional diagram one need to consider when you make the calculations for their interactions. So then, after we have the quarks, different colors and different flavors, and we can make them to be our matter, like the baryon, and the meson. So quarks and antiquark pair will compose the meson. For example, the pion, the kaon, and other additional heavier mesons. And for baryons, the most known is proton and neutron. And the proton is heaviest, the lightest one of the baryon, and if this baryon number is conserved, so now we conceived, or in this theory or in the Standard Model, the baryon is the proton is stable in the universe. But in the grand unification theory, proton unstable, can decay to other particles. This is the compelling evidence, if it's observed, of this unification of the strong and weak and the electromagnetic theory of the grand unification theory. Then the confinement, since the colored particles have never been observed, so these people conceive that the property of this QCD is very unique. The colored particle cannot be isolated, and only the color neutron particles exist as a free particle. And the model of this is the coupling will be getting stronger when their distance will be getting larger. So they cannot be getting far away or infinite distance. And the confinement can also tell you the creation of the new particles from the inner part of this meson or hadron. For example, we have this as for example meson quark and quark pair. If we use energy to make its distance to be larger, but some additional quarks will be created inside this by using this additional energy. So finally, we will come up with two additional pairs of quarks, but with also the color neutron way. So that means this explains the phenomenon of the confinement. Why confinement exists actually is, well, firstly, for this, the prediction for this process of this quark pair creation inside the nuclei. Actually, there will be some different jets in experiment. For example, the 2 jets or 3 jets in the experimental process, and this also has been observed in 1960s and 70s. I think 3 jets in 70s by the Petra storage stream. And the reason of this is asymptotic behavior of the QCD. Actually, it's have very strong interactions. So the coupling is at order of 1. So the Fs is a coupling of the strong interaction. So in this way, similarly as we shown for the QED, we can have some additional diagram for the same process, and 1 loop, 2 loop. So in this way, you can see the amplitude of these three are almost the same at low energy region. So that means we cannot do any kind of perturbative calculations. So I need new ways to do this. For example, the lattice QCD. And the evidence or the theoretical argument for this is based on also another behavior of this QCD interaction is another end of this. That means at a higher energy part or in the short distance region, the QCD is asymptotic free. So that there is evidence that this strong coupling constant Fs is not a constant, but it will the size of this is depends on the distance or depends on the energies. So for the high energy, the Fs will be going to smaller and smaller. So in this way, for the high energy QCD is calculable in the perturbative way, and so the end of this will be in the very low energy part. The QCD is non-perturbative, so it can the current one very difficult and high computing power needed process is lattice QCD calculation to. So sorry. to make the low energy QCD prediction for the different processes. Or for the electron wake part, and then, yeah. I just run some about the QCD since I don't know, I cannot do any calculations for this, so just some ideas. But I think we can use some time to mention about the electron wake part of the model. It's gauge theory or gauge invariance theory plus the Higgs mechanism, the spontaneous symmetry breaking. So for this electron wake part, actually based on the gauge symmetry of SU2 times U1, and so the particle contains the same using quarks and the leptons. And the most important part is the Higgs mechanism to rescue the problem we just mentioned in the non-abelian gauge theory, that the intermediate gauge boson cannot be massive, cannot have mass because of gauge invariance theory, gauge invariance requirements. But there is some special mechanism that we can give mass to the gauge boson by this spontaneous symmetry breaking, not explicit symmetry breaking. And a very simple example for this the Higgs mechanism, but not in our STEM to SU, the electron wake part, but in the U1 part, actually, this can be done by this so-called scalar QED, only our U1 gauge fields and also a scalar. Yeah, you can show this way. Yeah, we have the covariance derivative here, and this is defined this way. And the scalar potential is very simple. It's only the mass term, the quadratic term. And then we can, based on the gauge invariance, we can have this gauge transformation, and for this scalar field and for the gauge fields. And so here this gauge invariance, similar as I have shown for the U1 gauge theory, but even simpler than that one. So you can see the gauge transform for this total term only have additional phase as the field itself. So this will ensure the invariance of the whole Lagrangian. So this will be the critical part for the spontaneous symmetry breaking. So if this is the complex field. If the minimum part of this has some non-zero constants, this is the so-called the vacuum. And we can decompose this complex field with this vacuum part with some additional dynamical fields, the real part and the complex imaginary part. And if this the minimum of this potential have non-zero value for the web, so this will be give you the addition, to give you the part for this spontaneous symmetry breaking. I mean, for this there will be a phase transition from this from zero to non-zero if this mu term to be from negative to positive. This is give you the spirit of the spontaneous symmetry breaking. We can show it in a clear way that this is a famous Muscon hat, but in this in the 2D part, not a 3D part. And you can see the Lagrangian itself still respects the gauge invariance, but the vacuum itself is not. This is the key point for this spontaneous symmetry breaking. Let's see, if the web of this is zero, actually, if you multiply by additional phase, it's also zero. So it means it's still invariant under the gauge transformation. But if this is non-zero, have non-zero web, actually this will be not the same after the gauge transformation. So that means the vacuum state is not it's no longer invariant under this. So this is the main idea of this. The Lagrange itself still respects the gauge invariant, but we do it in our vacuum, in our lower sanity state to be breaking. Okay, then we will show it. I will stop at probably after 2 or 3 slides, and then we can rewrite this in this way. So we will have the real part and the complex, the imaginary part for this scalar field, and the gauge transformation will be going this way. So this part will be eliminated to be a real part, and then we will the spontaneous transformation for the gauge field for this additional derivative of this imaginary part. So this, in other words, give a redefinition of this scalar field and the gauge field. So that means we have this additional term in the gauge field. And then we can calculate the potential. So this real part of this have additional h square part. This will give you the mass of this scalar field. And there will be also some additional H3 term also. And in addition, we can calculate the mass term of the gauge field by calculate the current derivative term. You can see there will be some additional term of the mass term for the gauge field, A prime, to give you the mass of this. So we know for the massless gauge boson, like the photon, it only has the transverse component, so it will have a 2-degree freedom. And so that's why it is massless. When we have this additional component of this, sometimes people say that it's eaten up by this gauge field. So then it means it have additional longitude component. So this longitude component will finally give the gauge boson non-zero mass term for this. So this is the key spirit or key part of this spontaneous breaking to give the gauge boson finite mass. Okay, yeah, I think I can stop here. This is an example for the Higgs mechanism spontaneous breaking. I will come back to this tomorrow by starting with our SEM model case. So thank you. Yeah.
Thank you, Yufeng, for this great review. So please, questions? Yeah. The lady was first.
Do you think any law or statement have a potential to be included in standard model in near future?
Oh, you mean in the near future, how to go beyond standard model to add some new integrant or principle? Is your question?
Yes.
I think I will tell some of these tomorrow. For example, how to unify the different coupling. For example, in the high energy part, as we shown in the QCD, the coupling constant will go in smaller. The asymptotic freedom give us the strong coupling will be going smaller, and the others will be going up. So in the very high energy part, this will be unified to one single coupling. So this is one direction about the gas theory, grand unification theory. This is one. Another, I don't know, for example, supersymmetry is another, it's also a long history, but there's still no evidence for this. But theoretically, it's a beautiful one to solve the problem, for example, naturalness or gauge hierarchy problem or others, even the supersymmetry particle for the dark matter. Yeah, I will show the drawbacks of the STEM model tomorrow. Yeah, okay.
Thank you, Ben. We will play.
Okay. Okay, thank you for your question. Okay.
Thank you for thank you very much for the presentation. I have one question.
Yeah.
What phenomena show a violation of the standard model if with its have, and is its modification expected?
So what kind of law you want to break? You mean?
He's asking if there is any violation of the standard model.
Oh, neutrino mass. And neutrino mass is, by definition, actually it's not a huge or large violation of the standard model, but that means at that stage, there's no right-hand neutrino in the experiment part. So that's by definition, it's neutrino mass is not exist in the standard model construction. So
What mass?
the neutrino mass. I think yesterday evening there is a discussion about the neutrino oscillation requires the non-zero neutrino mass.
Okay.
Yeah, but if neutrino mass is, it can be either the Dirac type or Majorana type. But if it is Majorana part,
It's only
yeah.
It's only phenomena. Only its phenomena.
Is this the only?
no, a dark matter is also not exists in the instant model. It's another one. If from the experimental parts, I think these two are probably there are some additional, but these two are the major experimental indications that we need to go beyond standard model.
Thank you.
Okay. Yeah.
So I have wanted to ask about the decreasement of constant of strong interaction.
Oh yeah.
Is asymptotic freedom connected with anti-shielding of color charge due to gluons have color charge as well? So when two quarks bind together,
Yeah.
and the distension between them less than before, there are asymptotic freedom, but also we have this anti-shielding of the charge, color charge. So if we measure this charge, we will measure the less value, some kind of value.
So what kind of measurement you want to do? You mean to measure the?
So how does asymptotic freedom? How is asymptotic freedom connected with the anti-shielding?
Anti-shielding?
Anti-shielding.
Okay, anti-shielding. Yeah, so I don't know. You think anti-shielding can be measured in some way?
No, he's asking if there is any relationship between asymptotic freedom of quarks.
Yeah. Thank you. Yeah. Sure. Asymptotic freedom is also calculated using some. I don't know. I don't have time to say it in the. Yeah, it's calculated by adding the lobe part and also to calculate the beta function. That is some shielding or anti-shielding effect of this. So to calculate the beta function to be negative accurately, and then prove that the QCD is asymptotic freedom. Yeah, I think this is the same effect. Yeah.
Okay, thank you.
Okay, as you mentioned, we cannot obtain free quarks in the experiment.
Yeah.
So how do we measure the mass of quarks?
Okay, it's a good question. Yeah. The mass of the quarks in the nuclei. Yeah, some light ones are made it in some calculation. I think up down is.
Magnetic moments.
Yeah. Oh, you mean magnetic moment can connect to this? Okay, thank you. But top one is can be measured directly since for the low part it's I think Dima is correct that it can connected to other measurements. Then you can extract the mass of these composite quarks. Yeah.
You said magnetic moment?
Yeah, magnetic moment of the nuclei. Yeah.
Okay, thank you.
Some questions from the other side. Okay, come on, guys. What's wrong with you? Okay, another one. So
This is symmetry breaking.
Symmetry breaking. Yeah.
Okay.
Okay, I've got the very last question. Probably, if no one is volunteering. No. Okay, about the gauge symmetry.
Okay.
Suppose we make a gauge transform,
Okay.
and then the wave function of a fermion, like an electron, for instance,
Okay.
requires a phase.
Yeah.
On the one hand.
Yeah.
On the other hand, we know that the people electron optics are able to measure phases of the electron wave functions nowadays.
Okay.
Does this violate the gauge symmetry of QED or not?
Okay. It's quite difficult. I think it's not, but the reason is not so simple. I think.
Experimentally they see the difference of phases.
Yeah.
Okay. So,
Which is gauge invariant.
it's not the phase of gauge gauge transformation.
He cheated you.
Okay. Sorry.
Somewhat.
Okay. Okay. Thank you.
Thanks.
Anyway,
So
thank you.
let's
Yeah.
thank the panel.
Yeah.